Hello, I'm Dr. Simon Romero and I'm here to talk to you a little bit about the dot product. The dot product is a very important operation between vectors that we are actually going to use the entire semester. We're going to start with the idea of the dot product, the angle magnitude definition of the dot product, component definition of the dot product, direction, angles and cosines, and components and projections. As always, I suggest you to do all the practice problems so you can detect whether you are understanding this very important concept or not. The idea of the dot product is relatively simple, but it has some details that you have to be very careful to consider. We want to define a product of two vectors to be a number that measures into what extent they point to the same direction or not. Let me give you an example. In this case, we can think that the two vectors have compatible directions. In other words, they are kind of helping each other. In this case, we want the dot product to be positive. In the case when they have incompatible directions, we want to have the dot product to be negative. In the case when they are not helping each other, they are not hurting each other, we are going to want the dot product. We want the dot product to be 0. In every case, it seems that the angle between the vectors is the factor that distinguishes each situation. When it's positive, the angle seems to be acute. When it's negative, the angle seems to be obtuse. And when it's 0, the angle seems to be a right angle. If you remember, we have a trigonometric function that actually behaves more or less like this, and that's the cosine. When it's acute, it's positive. When it's 0, when you are in the right angle, and when the angle is obtuse, it's negative. So the dot product seems that the cosine is going to play an important role in the dot product. Let me give you the angle definition of dot products. Before doing that, let me just tell you that remember always that a vector dot a vector is always going to give you a scalar. So in other words, the dot product of two vectors is always going to be a number. Dot product, the angle magnitude definition. If you have two non-zero vectors, we define the dot product as b dot w to be the magnitude of b, the magnitude of w, and times the cosine of the angle between them. If one of the vectors is 0, then the cosine the angle between them doesn't make sense to talk about the angle. We define the b dot 0 to be equal to 0. We're going to say, here we come to a particular definition. We're going to say that two vectors are orthogonal if the angle between those two vectors is pi over 2. The way that we're going to represent that algebraically is going to be when the dot product of b and w is equal to 0. So if the angles are orthogonal, immediately we have to think that the dot product is equal to 0. Let me give you the component definition of the dot product. Given two vectors and you have the components of the two vectors, then b dot w is equal to b, the first component of b times the first component of w. Then we multiply the second component of v with the second component of w, and then the third component of v with the third component of w, and then we add everything together, and that gives you the dot product. So the question is, are these two ways to computing the dot product equal? Well, in the class activity that we're going to have next class, we are going to see that effectively these two methods to compute the dot product are the same. The difference is that this component definition is way more useful because usually we're going to have vectors given by components, and not always is easy to compute the angle between vectors. So in this one, this definition is going to be way more useful. Let me give you some properties of the dot product. If u, v, and w are vectors in R3 and c is a scalar, this is what is going to happen. This first one is very important. If you take the dot product between two numbers, then the result is the magnitude square. And you can see using either of the definitions that that's the case. So one very common mistake is writing this. Please don't write this. This doesn't make sense. This is wrong. P dot W is equal to W dot B, so that means that this operation is commutative. In other words, it doesn't matter which one you take the dot product. I mean, which order you take the dot product. Is distributive, that is the one that we have right after the commutativity. This is the commutativity. This is distributive, that it says that you can take common factors or you can FOIL using the dot product. The other one is if you take a scale version of B and then take the dot product with W, is the same as scaling first W and then B, or multiplying C by the result of the dot product. This one we already talked a little bit about it, and this one at the end is going to be that the largest that the absolute value of the dot product can be is the magnitude of B times the magnitude of W. Let me give you some applications of the dot product. One of them is finding the angle between vectors. Let's try to do this problem. Find the angle between the vector B and the vector W. And now the thing that you have to notice is that since the components of the vector B and W are given, we can use the component definition of the dot product. In other words, I'm going to compute the dot product using those components. So we have that B dot W is going to be equal to 1. Now that we have the result of this dot product, the thing that we can do is we can use the other definition, because the other definition involves the angle. So we can find the angle, because we already have the dot product, by just solving for the angle. So notice that in here our dot product was equal to 0, but on the other hand we have that the dot product is equal to the magnitude of B, magnitude of W, the cosine of the angle between them. So we have that the magnitude of B, magnitude of W, cosine of the angle between them is equal to 1, so the cosine has to be equal to 1 over the multiplication of the magnitudes of B and W. Now we just compute the magnitudes of B and W, and we obtain that the angle is the arc cosine of 1 over 3. If for some reason you cannot compute arc cosines, or this in particular is an inverse cosine that we cannot actually compute without a calculator. So if that's the case, you should leave it indicated just like I did over here. In the case that you have one of the angles that we can compute the inverse cosine, you should do so. Let me talk a little bit about projections. A projection of W into B is the vector obtained by dropping a perpendicular line containing B from the tip of W. Now, let me repeat that. I am saying that is the vector obtained by dropping a perpendicular line to the line containing B from the tip of W. I'm sorry about that. So in graphical it's very easy. You just drop a perpendicular line to the line containing B, and then kind of like the shadow vector that you obtain is going to be the projection of W onto B. For example, in this other case, you take the line containing B, drop a perpendicular starting from the tip of W, and the shadow that you obtain is the projection of W onto B. Here are the two cases, and the thing that we're saying is, before continuing, let me just tell you really quick how this notation goes. The vector that you are projecting is the one that goes in full size. The vector that you are projecting onto is the one that goes in the subscript. So note that if the angle between the vectors is acute, the projection and B have the same direction. Notice that this is kind of like, it's going to have a relation with the dot product, and you will see what's the relation later on. Now, if the angle between the vectors is obtuse, then the projection and B have opposite directions. Now, could you tell me during class, or just think about it, what happens when you have a right angle? What will be the projection? Well, I'm going to move on. The components. The component of W into B is the sine magnitude of the projection of W onto B. In other words, the absolute value of the component is equal to the magnitude of the projection. Let me explain a little bit more what do I mean by sine magnitude. So this is the component. For example, in the other case, when they have an obtuse angle, That's going to be the component. Really quick, when I talk about sine magnitude, what I mean is that the angle, if the angle is acute, the component is going to be positive. In other words, if the projection and B go to the same direction, they are going to, then the component is going to be positive. In the case that you have an obtuse angle, the component is going to be a negative scalar. Notice that this is just like the dot product. So if the component is positive, the angle between the vectors is acute. If the component is negative, the angle between the vectors is obtuse. Let me give you the formulas. The formulas are going to be like this. I mean, you may notice here that the dot product plays a very important role to determine the sign of the component. One way that you can remember this is the component relies on whether the B and W are helping each other. If they are helping each other, that means that the dot product is positive. If they are hurting each other, then or they are going against each other somewhat, then the component is going to be negative. And the projection is just going to be this one over here. Again, you may wonder, well, how these formulas are the way they are. Well, that we're going to see in the class activity, so don't miss that one. Once you know where these formulas come from, they will be very easy to recall. It's just a little bit about trigonometry. Let me give you an example. An example is find the component and the projection of the vector of that vector 2i minus 3j plus k onto the vector I plus 6j minus 2k. Now the thing that you have to remember is that it is very important to, if you want to use the formulas, to check what order, I mean, who is W and who is B. And the thing that you have to remember is that the vector that you are projecting is what we're calling here W, and the vector that you're projecting onto is what we're calling B. So in this case, the vector that you are projecting is this one, so that will be W, and the vector that you are projecting onto is going to be B. Once we have that, we're going to apply the formulas. The easiest formula to remember is the component, so let's try to do that one. So the component, given that the dot product of B dot W is equal to negative 19 and the magnitude of B is equal to square root of 41, then we have that the component of W onto B is negative 18 over square root of 41. Now, we can use the same information to compute the corresponding projection. So the thing that we have is the projection of W onto B is going to be just minus 18 over, and instead of having the magnitude of B, you have the magnitude of B squared, so you will have 41 instead of square root of 41. That's one of the difference, and the other difference is you are multiplying by the vector B. And notice that in this case, you obtain a vector that goes in the opposite direction of B. Remember that you can always pause this video, you can go back, you can review, and please let me know if you have any questions. Thank you very much, and have a good one.